every time a jet roars down the runway and lifts into the sky. It's obeying laws of physics, hidden inside the shape of its wings. A wing is called an airfoil, curved on top, flatter on the bottom, built to interact with air rushing past at hundreds of miles an hour. As the wing slices forward, air splits at the leading edge, one stream flowing over the curved top, another beneath the flatter bottom. Pilots tilt the wing slightly upward into the airflow, an angle called the angle of attack, and that tilt changes everything about the lift produced. The steeper that angle, the more the wing shoves air downward as it passes, and the stronger the upward force pushing back on the wing. But angle of attack is only part of the story, because the wing's very shape also plays a powerful role in generating lift. Over the curved top surface, air accelerates, moving faster than the air gliding along the flatter underside of the wing. Daniel Bernoulli, an 18th-century physicist, discovered that faster-moving air exerts lower pressure than slower-moving air nearby. So the fast air above the wing creates a zone of lower pressure, while higher pressure builds underneath the wing. That pressure difference pushes the wing upward, from the high-pressure zone below toward the low-pressure zone above. But pressure alone can't explain everything, because even a flat wing tilted into the wind can still generate lift. That's where Isaac Newton's third law enters the picture. For every action, there is an equal and opposite reaction. As the wing's shape and angle push a stream of air downward, the air pushes back upward against the wing with equal force. This downward deflection of air, called downwash, is a direct source of lift, working alongside the pressure differences above. Neither Bernoulli's pressure explanation nor Newton's reaction force stands alone. Together they describe the same single physical event. Engineers now understand lift as one unified phenomenon, air bending around a wing's curve while being forced downward at the same time. Both explanations are two views of the same underlying physics, the wing shoving air down and pressure differences arising from that motion. Lift doesn't stay constant. It grows dramatically as an aircraft speeds up, since faster airflow multiplies the pressure difference many times over. Wing size matters too. A larger wing surface pushes more air downward, generating proportionally greater lifting force for the aircraft. Air density changes lift as well. Thinner air at high altitude produces less lift than the denser air found near sea level. Push the angle of attack too far, though, and smooth airflow over the wing breaks apart into violent, swirling turbulence. This sudden breakdown is called a stall. Lift collapses rapidly, and pilots train constantly to recognize and recover from it. Wing shape, engineered with extreme precision, determines exactly how much angle a pilot can safely use before that airflow separates. To manage lift throughout a flight, engineers built moving surfaces directly into the wing that pilots extend and retract. Flaps extend from the trailing edge, increasing the wing's curve and surface area, generating extra lift for takeoff and landing. Slats extend from the leading edge, smoothing airflow at steep angles, delaying the stall so wings keep working at slower speeds. During takeoff, pilots extend flaps fully, trading some speed for maximum lift, letting heavy aircraft leave the ground on short runways. At cruising altitude, wings retract to a sleek, efficient shape, since less lift is needed once the aircraft reaches steady speed. On approach, flaps and slats deploy again, slowing the aircraft safely, while keeping enough lift for a smooth, controlled landing. From ancient dreams of flight to modern jets, it all comes down to a wing's curve, its tilt, and the air it commands.